Hi, this video we're going to start to learn about frames. Frames are made of different structure members. This is example of it. As you can see, this is made of ACE, which is a L-shaped structure member, and you also have a BCD, right? This another, and also you have this DE, which is just a straight line. So there are actually three member. Here I'm going to color code them. So you have BCD, and you have AL, ACE, you also have DE. Those three members, and they are connected. They are pinned at point C right here, and also pinned at point D, and pinned at point E. So when you study a frame, we needed to be aware of few things. First, you look at FBD. When you look at the FBD, you have a lot of options now. You have FBD of the entire frame, the whole frame, which for this case will be this entire frame right here, right? Or it's gonna be your individual, each component FBD, each member FBD. For that situation, we will potentially, for this particular one, we'll have three of them. We will have BCD, and we also will have, ACE, and we also have DE. So that's the first thing I want you to look at. You've got options for FBD. Then another thing we need to be aware and use for frame is going to be to recognize the true force member. We're talking about before, true force member is when you have a member, regardless what shape it is. For example, I have an L shape here, and as long as there's only forces applied at two different locations, for example, A and B here, then that is a true force member. And true force member are going to be make sure they are equal and opposite, and also collinear. Basically, you connect A and B. Either for this is going to be tension, or you can be, this member can be compression. It doesn't matter, right? And here it's just assumption you made. So that's a second aspect when you're solving FBD. The third one is you are going to use Newton's third law. Newton's third law, we all know it's every action have equal but opposite reaction. So what does that mean is if, for example, here at C, right? And let's just point in this point C here. And the force exerted, for example, at C here by the member, this ACE here, right? On this member BCD, So this red line is exert the force to this blue line at this pin C here. And this force has to be equal and opposite to the force, this blue line BCD exerted on the red line ACE. Okay, so that's Newton's third law, and that's you are going to use for frame. Now here's the answer here for this problem. Now let's look at how do we solve this. Members ACE and BCD are commonly are connected by pin at C and by the link DE. For the loading alone, determine the force in link DE and the component of the force exerted at C on member BCD. Okay? So when you read this, exerted at the C on member BCD, where's that force coming from? Force basically coming from your ACE, right? So it's basically ACE apply force to member BCD at C. Okay, and when they ask you about the force link at DE, then first we identify is there any true force member here. They are made of three members. Is there any two force member. Now let's look at it. BCD is not going to be two force member. Why? Because there's a force at B here. There's also force at C because that pinned. There's also pinned at D, so that's 3 force. That's not 2 force. And how about our ACE here? ACE, same wise. There's a pin at A and a pin at C and a pin at E. That's again at 3 different locations. However, how about DE? There's a force at D and a force at E because they are pinned connection. Yes, that's exactly 2 force member, 2 separate location. Then we know the DE, if we were to look at FBD of DE, I don't know what number, let's just see, leave alone. So if I have DE here, then when we draw the force, if I consider this D is being compressed, so they are going to be connecting D to E on that line and compress that DE. That's 2 force member here. So when they ask us the force that link DE, basically is asking this force right here. And we can just call FDE here. And this is also FDE, that equal and opposite. Okay? So far we recognize a 2 force member, and we start to work on each member free body diagram. However, from this FBD, we cannot really solve the problem. We know they are equal, but we cannot solve it. So what do we need to do is we potentially gonna look at the whole frame. Okay, so here I'm going to start this problem by looking at FBD number 1. Number 1 is going to be my entire frame. So for the entire frame, what do we have? We'll have this ACE in red. Then we also have this BCD. Then we'll have our DE. Then let's go ahead and label them DE, and we'll have our ACE, then B, C, D. All right, so for this entire FBD, we have learned before. For example, D and E will not have any forces on there, even though they're pinned, because we're talking about this entire frame in contact with external environment. The only external loading will be at A because it is a pinned support. So we will draw AX and AY. Same thing for B, right? B is a roller support. So it can move freely at a vertical direction, but it cannot move at X direction. So we'll have a BX or B. Then again, emphasize again, there's no forces at C or D or E because they are internal connection. Those internal connection will have forces on there only when you dismember them, when you look at each member. Because when you look at the entire FBD, there's no forces on this point. Just like a table is supported by the ground, we don't worry about the table, how the tabletop is connected to the legs, right? There are screws, there are wood glue there, but we don't worry about the connection. We just worry about the entire weight of the table and the normal force supported by the ground. So hopefully that helped you understanding about that concept. So now let's look at this FBD. You have how many unknown? We have 3 unknowns, AX, AY, and B. Then 3 unknown, we know this is a 2-dimensional problem. 2-dimension equilibrium, we have 3 equations, right? And then we can solve those 3 unknowns. So first, sum of forces at X, we'll have AX plus B, both positive, going to the right, equal to 0. Sum forces at Y, we'll have AY equal to 0. I think I missed one force here. I forgot that 480, so I'm going to put 480 right here. And 480 seems to be exactly on the top of E, so oops. Okay, so I'm going to draw that force at E right there. So that's our 480 Newton. Then I need to go back over here for our AY. We'll have minus 480 since it's going downward. That's equal to 0. Then we'll have our moment equation. We choose A because A have a lot of forces down there. So we'll have B. This B, the moment of arm for that B is going to be this distance right there, right? And that distance, that rainbow color, is going to be 60. Oh no, actually no, sorry. It's going to be 160. And thinking about that rotation, that's counterclockwise, so that's positive. Now let's look at 480. And our 480 have its own moment of arm as well. And that 480 rotating about A, then moment of arm is distance, and that will give us 100. And that's a clockwise rotation, so it's going to be minus. That equals 0. So from, you can go ahead using calculator or online to solve those three unknown, like how we did before using Wolfram. But also this one seems to be straightforward to solve it. So A1 will have 480 from equation number 2, and from B, we can solve B from equation 3. Then we'll have what, 300? B has 300 Newton. And since we find our B, we can go ahead and solve our AX. So our AX is going to be equal to negative 300 from the first equation. Then you got reaction supports using entire FBD, right? But remember, keep in mind, what do we need to solve? We need to solve FDE. We also need to find out the force ACE member apply to BCD member at pin C. So basically we need to find the C, internal reaction there at C. So we really needed to do what? We needed to look at each member. We already did for one, that two force member DE. Now let's go ahead to look at some remaining member. So if we look at FBD number 2, let's think about it. If we, here you really can do either one. I mean, you can either choose BCD or ACE. If I were to choose this ACE, oh, my ACE is color red, right? It's trying to make it consistent. So you have A right there, E, ACE, okay? Now you dismember them, right? And you isolate this L-shape ACE out. Now those internal connection, for example, at C and at E, when they are connected with other members, they're exposed, which means, yes, there are forces on there, on that member, okay? So we're going to consider those internal force now because we're looking at just one individual member and they are connected with other members apply forces onto it, and that's their, for this particular isolated member, those other forces are external forces now. Okay, so let's go ahead and draw. At A is pin support, and do we already know them? So that's actually another thing I want to add on to our frames characteristic. Not only you look at the FBD, look at two force member and Newton's law, and it's actually you can you will actually encourage and or maybe necessary to add forces solved to next FBDs. What I mean by that is you solved AX and AY. So add those reaction support you solved into the next FBD right here. Since we know AX is negative 300 and our FBD number 1 is pointing to the left, that really means the true direction is going to be pointing to the left, all right? So make sure that's going to be in the correct direction now, because you actually put the numbers in there and we're going to put the direction correct. So here made a note, add forces solved and with correct direction. Okay, so that's what we just did. And we also have AY. AY we pointing up for FBD1 and we got positive, so it is indeed going up and it's 480 Newton. Now let's look at C. C is pinned, right? And we're solving actually C right here. So we're going to assume the direction. If we assume CX and CY in this direction, and also we needed to solve D at E. And E here, we might be attempted to draw EX and EY. If we do that, we are ignoring this beautiful fact we have over here, two force member, which you have figured out here. So I'm actually going to call this FBD number 3. Because from FBD number 3, we know DE is a two force member, and we assume DE is being what? Compressed. Yes? If DE is compressed, if I were trying to use a dash line to kind of show where DE is, right, in this FBD. So if DE is compressed, what I mean, where is that force coming from? Which means this ACE is compressing DE at point E here, this way. If DE is being compressed, remember we said this third law? DE gonna do what? DE gonna push ACE back at E the opposite direction. So it's gonna be going that direction. Okay. So here I'm gonna ignore, get rid of D and here because when we look at ACE. So this is very critical. So thinking about this line here, why do we have this particular? Because this line and this is a pair. It's Newton's third law. You know, here DE, this force DE is applied by this L shape ACE. And then this DE is gonna push it back, you know, the other way. Okay. So knowing that, we are going to, any other forces on this ACEL shape member? I think no, right? Then we'll have those, I'm going to label this. This is basically our FDE, the same magnitude, because Newton's third law, equal opposite. So FDE is what we're solving, CX and CY is what we are solving. Perfect. We have 3 unknowns. Have we go ahead and draw E at EX, EY, then we'll have 4 unknowns, and we're ignoring the fact it's DE is a two force member. And that information has to be used, right? And now let's look at DE. DE is gonna be, we're gonna look at the dimension. Here is 150 horizontal, and vertical is 80, so it's 80, 150. And obviously that can be simplified. If we divide it by, let's think, looks like we can only divide it by 10. So it's 8 and 15. 8 and 15 is at a particular triangle. So 8, 15 is actually a right triangle. 8, 15, 17. So translate that slope right here. So we have 8 vertical and 15 horizontal and 17 for hypotenuse, right? Okay, so we have this FBD made. We are ready to solve. So it's again 2D equilibrium problem. So we have 3 equations. Forces at X and 300 going to the left. negative 300, Cx point to the right, positive, and FD have X component, that E. So I have minus here since that's going to the left, that equals 0. Then forces of Y will have 480 going up, so it's positive, and we have CY positive going up. FDE is going downward, right? The Y direction, so it's 817 FDE downward, so it's negative. That equals 0. Then if we look at moment, and we can do moment at A. Oh, actually, I think do moment at C is the best. Why? Because we can get rid of CX and CY. So here, moment at C. Then in that situation, look at this 480. 480 going 3 point C, right? So that's moment of arm is 0. And now let's look at 300. 300, and then times moment of arm, rotating about C, so it would be this. How about AC? What's the AC length? Which is 160 right here. And now let's think about direction. That's 300 Newton right here, rotating about C. That's counterclockwise, so that's positive. Then we just need to look at FDE here. Well, even though FDE is written this way, I can feel free to move over here. Why is that? Because it's applied at E here, right? It's applied at E. So when you look at this force, which is slanted, you're going to, decompose X direction and Y direction like how you did over here. Now let's look at X direction force, which is 15, 17 FDE. And if that force is going to rotating about C, and moment of arm is going to be this length. Moment of arm for that is going to be this 80, corresponding the height, so times 80. And that is this force rotating about C. It's clockwise rotation, so that's going to be negative. Okay, because it's clockwise rotation. Now we're going to looking at the Y direction, which is right here, and it's 817 FDE. And the moment of arm for that correspondingly will be this horizontal length. And what's the horizontal length right here? That's our 100. So times 100. And now thinking about the direction, the rotation. This force is going to rotating about C, and it's also clockwise rotation, so that's negative. All of those together is going to give us equal to 0. So we'll have 3 equations as well, and let's see what we have. Again, for this problem, it's probably easiest to go to equation solver to go ahead and do that. So here we are going to go to the offering. Hopefully you are solving that yourself. Feel free to pause. And then we have negative 300 for the first equation. Then plus Cx, I'm just going to use x, minus 15 over 17. FDE, so I'm just using F. That's equal to 0. First equation. Second equation, 480. Plus y, cy, minus 817 FDE, that equals 0. Then the third equation is 300 times 160, then minus 15 over 17 FDE, so it's F, then times moment of arm for that is 80. Minus 817 FDE, then we're going to times 100. That equals 0. So let's try. Hopefully our input is correct, and then we can verify it, the equation, first and the second equation, and the very last equation is right here. I think there's something not right for the last one because I have 300 times 160 300 times 160 minus 1517F times 80 minus 817F times 100. Okay. Oh, okay. I know what's the trouble now. They think this F is the Fahrenheit. It's a Fahrenheit, so that is a problem. Then what can we do? Instead of using small big F, am I going to try that? I'm going to try small f. If we do that, I'm going to change all of them to small f. And I have a hint. I feel like this might work even with big F. Maybe because I didn't do the asterisk 100. Okay, now everything looks good, and we have our answer here. We can take a picture and bring that numbers there. So from what I have here, I have this FDE equals 408. And that's going to be Newton. CX is equal to 660. And the CY is negative 288. So now I have these answers, and I was quite perplexed because my answers are not right. This was a correct answer. And I stare at it, and then I have to tell you. What happened is my moment arm for this A is wrong. And for moment of arm for AX, rotating about C should be this distance, right? And that distance is AC distance. What I read is 160 only. Should 160 plus 60. All right, so let's make that change. So it's 160 plus 60. And that should do, we can go to the wolfram, and it's this value. Plus 80. Then we can try. Then we have the answer right here. Let's see. Oh, it's 160 plus 60. Okay. Third time is a charm. All right, we got the correct answer. Okay. So that's not right. And our FDE, after that correction, we have 561, and the CX is 795, and Y is negative 216. So what that tells us is FDE is in the right direction, what we have written here, right? So it is indeed going down at downward to the left direction. CX is positive, so we had that right. And our CY, it should be going downward. So that's all. So far we have built 3 FBDs, and we got all the answers we need because we know the force at link DE, that's going to be this value. And the force exerted on C on member BCD is basically going to be this value, Newton's third law. Some of you might be wondering, can I use FBD number 3, which is instead of ACE member, can we look at the BCD member? Yes, we can. You can go ahead and draw the BCD member, you should get the same answer right here. So you have BCD, right? And for BCD member, we'll have a different forces because we know, so here's OR. If we use BCD, B has a roller support we calculate in FBD1, it's 300. So that's going to be 300. And also, we do not know the reaction support at C, so we will have CX and CY, right? And then at D, we also have this FDE. Again, using Newton's third law, because we can look at this one. At D now, if FD is applied at ED member this way, ED going to be pushing it back, at BCD upward, so it's going to be that direction. That's our FDE. Then we'll also have this external force, 480 Newton. So if we were trying to do 3D equilibrium on this one, we'll have some motion, 2D equilibrium. So we have forces at X, we have 300 to the right and CX to the right, and FDE have the same dimension, 8, 15, and 17. So it will be 15, 17 FDE equals 0. Same thing for force at Y, we'll have CY minus 480. Then plus 8, 17 FDE equals 0. Then we'll have moment. If we do moment at C, and then we have 300, and the moment of arm for the 300 should be this distance right here. So it's BC vertical distance. That's going to be 60. And that rotation is clockwise, so it's negative. Then we have this 480. 480, the moment of arm will be this, right? Horizontal distance from C to this force is applied. That gives us 100. And that is clockwise rotation, so negative. Then we have FDE, our X direction and Y direction. X direction does not cause moment since it goes through C, and the Y direction is going to be 8 and 17, our FDE. And the moment of arm will be this entire length of CD, which give us 100 plus 150. And that rotation is going to make it counterclockwise. So that equals 0. So go ahead. We can put that in the calculator. See what we have here. So the first equation we have is 300 plus x, that's cx, plus 15 over 17. FDE, we'll just use small f. That equals 0. Then the next is our cx minus 480, then plus 8 over 17 FDE, that equals 0. The last one we have negative 300 times 60 minus 480 times 100, then plus 8 over 17 times FDE, then times our 100 plus 150. That equals 0. Then we can enter it, see what we have. Okay. So somehow is not taking for it, and I look at it, the mistake, I have first one here, Y. It's gonna be Y, and let's click again. Okay. It is getting better, but it's not solving it. It's not solving it. All right, so a quick fix is put the asterisk between f and this constant, then we have a value. Okay, and this value essentially is the same one as the previous one, might have a difference in terms of a sign, and that's predictable because we assume different direction perhaps. So we have over here, from this calculation, we have our FDE as 561, and our CX is negative 795, and the CY is 216. Okay, so that is the same thing. All right, so hopefully that helps with the frame problem, and I'll see you on the next one. Bye.